Hello students, in my previous videos I explained the training algorithm of Adeline and Madeline. In this video I'll explain backpropagation algorithm. So what is backpropagation? I guess you guys already familiar with multilayer perceptron, but let me just remind you again. Multilayer perceptron is a feed-forward neural network consisting of multiple number of perceptrons interconnected parallelly. It mainly consists of three layers: input layer, hidden layer, and output layer. So the neurons in the input layer receives the input signals and pass it to the hidden layer units. The hidden units in the hidden layer process the input signal and generates output. Now, each neuron in the output layer receives the output generated by the hidden layer unit as the input and finally computes an output. Now, we already know, or I explained before, for training we need to give training data. Training data are basically your input data and label. Your label is the target data. So backpropagation is a method for training the multilayer perceptron. It is supervised learning and it is basically like delta rule. That means it will calculate the error. How will it calculate the error? By comparing the output with the target. So desired outputs are compared to the computed output and then system adjusts its parameters like weights and bias in order to minimize the error. Now the special thing about backpropagation is that it uses gradient descent with respect to the weight. Now I'll tell you about the gradient descent in later slides. So what happens in backpropagation? After you design your model or your neural network, you need to give training so that your model can correctly do a particular work, or it will be able to predict something, or for some classification work or pattern recognition work. So for that you need to give the training data with the label, which is the target output as explained before. So after getting the output, it calculates the error to see how far is your model output from the actual output. Then based on the error, you need to minimize the error. Now if the error is huge, then update the parameters, that is your weights and biases. After that, again check the error, repeat the process until the error becomes minimum, or you reach a condition where there is no more possible updates of your parameters. So after this training, your model is finally ready for prediction. Now we come to the part of gradient descent. Gradient descent is the most common optimization algorithm, and backpropagation uses gradient descent to minimize the error. So what happens here? It repetitively computes the error and checks whether it's a minimum error or not. If not, it will either increase or decrease the weight in small steps. It is a first-order optimization algorithm. This means it only takes into account the first derivative when performing the updates on the parameter. So, on each iteration, we update the parameter in the opposite direction of the gradient until it reaches a global loss minimum. Remember, initially we just randomly initialize weights and bias. Just forget about the bias for a while. Just think about the weights. So initially we just randomly initialize our weight. So initially the error is higher. So every time the error is higher, it either increase or decrease the weight in small steps until it reaches the global loss minimum, and it updates its weight value until it reaches the global minimum. Now, the size of the steps we take on each iteration to reach that minimum is determined by the learning rate. Here, learning rates takes a very important role. So, just see it carefully. The learning rate determines how big the step would be on each iteration. If your learning rate is very small, it would take long time to converge and become computationally expensive. If your learning rate is large, it may fail to converge and overshoot the minimum. So, too large of learning rate causes drastic updates which lead to divergent behavior, and small learning rate requires many updates before reaching the minimum point. Therefore, you need to just find a perfect learning rate to get your desired result. So most of the times this works, training process are experimental. So initially you just start with the small learning rate, then you try with a different learning rate to get the desired output. Okay, now we come to the backpropagation algorithm. So in the training or training using backpropagation, there are three main phases. Phase 1, feed-forward phase. Phase 2, backpropagation of error. Then third phase is updating of weight. If you see the network carefully, first your input signal is moved from 0 level to the n level until it reached output. So once your output layer units compute the output, it calculates the error. That means it's compared the output with the target output. And after calculating that error, it will backpropagate the errors from output layer to the hidden layers. Then on each layer, the weights will be updated accordingly. So in step 1, it's same. You just need to initialize weights and learning rate to some small random values. Then for every training pair, which is your score and your target function, you need to follow the phase 1, 2, and 3. So let's see what happens in phase 1. So each input unit receives input signal and pass it to the hidden unit. You guys already know there is no computation involved in the input layer. Input layer just receives the input signal and pass it to the hidden layer. Now in hidden layer, it calculates the net input using this equation. I am pretty sure you guys are already familiar with this equation to calculate the net input. So this is the equation for calculating the net input in the hidden layer. Here B0J is like your bias on the hidden units, and Vij is the weight on the jet input of the hidden layer coming from ith input of the input layer. Here I corresponds to the neurons in the input layer. So after calculating the net input, we calculate the net output at the hidden units by applying the activation function. Multilayer perceptron mostly uses nonlinear activation function. More generally, it's sigmoid function. So after applying activation function on your net input, it receives the net output at the hidden layer unit. So after that, send these output signals of hidden layer unit to the output layer unit. So here again in the output layer, first each of these units will compute the net input using this equation. Here wjk is the weight on kth unit of the output layer coming from the jth unit of the hidden layer, and b0k is the bias associated with the output layer. So after calculating the net input, it will finally generate an output by applying the activation function. Here yk is the generated output by the output layer units. Then the phase 2 begins. Phase 2 is calculating your error and backpropagate the error to the output and the hidden layer. So in the output layer, first compute the error correcting term in correspondence with the target pattern received at each output unit. So this is your error correcting term at the output layer. So let me explain you how you get this equation. So from this phase, the gradient descent part starts. First, we will see the gradient descent calculation for output layer, then we will move to the hidden layer. Now, to calculate the error, there are many different equations, but in neural network, more generally, use mean square error, and mean square error can be expressed in terms of this equation, which is just the average of target minus your output. So this error can be formulated as this one, tk minus yk, which is the target and the output value at the output layer unit. Now, as I already mentioned, gradient descent is calculating error in terms of weight, and it basically calculates the first order derivative of the error with respect to the weight. So in order to calculate gradient descent, we have to find the derivatives of error with respect to wjk in terms of weights connected or associated with the output layer units. So this term we can modify as this way using the chain rule. If you remember the calculus, mainly differentiation in your school days or college days, so whatever, so after breaking this term into this using chain rule, we can consider u as tk minus yk. Now just see the equation in different parts. There's nothing much to explain. You just see how everything is happening. Derivative of e in terms of u. After getting this, we finally get u, and derivative of u with respect to wjk, we finally get this term. Here tk is ignored because it's not directly related to wjk, so only this part remains. So this yk can be represented as the function of y and k, that is net input to the output layer. So from equation 1 and 2, we finally get the terms in these equations. If we replace the values for u, it will be this, and here is here, and finally we get the error term as tk minus yk into derivative of f into y and k. So after calculating this error term delta k, we update the weights and bias using this equation. Here is the error term alpha delta k and your input. This term is your gradient of weight and here is the gradient of bias. Then this delta k, which is your error correcting term, is sent back to the hidden layer. Now each hidden unit will be the sum of its delta inputs from the output units, and it can be represented as this equation, which is that means your input to your hidden unit in this backpropagation of error is the weight into your input error connecting delta k. Now in hidden layer, the error term can be calculated using this equation. I'll show how we get this equation. So based on this delta j, that is error correcting term in case of hidden layer, the weights and biases are updated using this equation. So weights is the learning weight into error correcting term into input, and bias is the learning weight in the error correcting term. These are the gradient descent of weight and your bias. So now let's see how we get this equation of error correcting term at the hidden layer. So we already familiar with this equation of calculating error, just like in the output layer. Here also same, using chain rule we can decompose delta gradient descent of error term into this equation. So similarly, from this term we get q, and from this term it's a bit lengthy because here the error term or the output is not directly related to your hidden unit terms. Therefore, this yk term you need to expand so that ultimately we get the term where it really associated with the hidden layer weights, because in this case we are taking the error in terms of the weight in the hidden layer, which is the Bij. Now if you expand yk term, it will be f y k. So derivative of this function is the delta of y and k. So in place of y, that is net input at the hidden layer, output layer, is this. So this term is a constant, so it goes away. Now just remain this part. Now again, using the law of derivatives, this term can be divided into derivative of qj and derivative of yjk, where wjk will be like non-related parts, so this part will be gone, so only term will left with the qj. Now in place of qj we can write as the activation function of your input weight at the hidden layer, so we just let it be here. So from this equation 1 and 2, if we put these values in this equation, we finally get this value u into this term. So in place of y we replace this term. Now see here, tk minus yk into f dash of y and k is your delta k. Remember from the delta k term we got in output layer. So for this term we just replace with delta k, and derivative of function q and j remains as just f dash q and j. So ultimately we get the error correcting term at the hidden layer as the error correcting term of the output layer into the derivative of the output of the hidden layer unit. So you guys just go through this equation carefully, you will understand. So next, in phase 3, you need to update the weights at hidden layer as well as in the output layer. So in the output layer, the weights and the bias will be updated by adding the gradient descent or the gradient of weights and bias with the old weights and bias, and similarly in the hidden layer as well, the weights and bias will be updated based on the calculated gradients of weights and bias at the hidden layer. So this process will continue until and unless it reaches the global minima, or maybe either the number of epoch weights or the target output finally matches the actual output, and this is the stopping condition. It's a bit complicated than the previous Adeline and Madeline algorithm, so I suggest go through the video and the equations carefully. You guys must know about the generalized delta rule. I already explained that or mentioned that in backpropagation as well. It uses delta rule. So generalized delta rule is nothing but that delta rule is extended to the hidden layer units. That's why it's called generalized delta rule. In perceptron, delta rule is only applicable to the output layer. So in multilayer perceptron, we have additional hidden layers. So same delta rule equations are used for hidden layers as well. That's why it is also called generalized delta rule. So I hope you understand. Thank you.